Okay, so today I'm going to talk about freshwater in the North Atlantic, freshwater fluxes in the North Atlantic. And just to acknowledge that this work was, as well as funding the rapid part of the wider 26 North array, NERC also fund associated science projects. So this project Monaco was one from the last round of rapid funding, and was focused on looking at the relationship between heat and freshwater fluxes across the 26 North section and the heat content north and south of the section. So that was the point of Monaco. The part of Monaco that I'm going to talk about today is freshwater fluxes across the section. Okay, so when I talk about freshwater fluxes in the ocean, or when I'm thinking about freshwater, what it is the integrated fluxes, the integrated exchanges of freshwater that the ocean has with the atmosphere, with the cryosphere, with the hydrosphere, and integrating that through the ocean. So the way we access that information is the salinity measurements that we make in the ocean. And because our salinity measurements are so good, we can get really quite precise volume fluxes of freshwater accessed through the salinity budget. So to calculate the freshwater flux, what we do is we take a section like the 26 North section, and we estimate the salinity flux across that. What we can do now, which is novel, is that we have time series of data across 26 North, which everyone's familiar with, I'm sure, and so we can calculate time series of those fluxes. We calculate the flux across this section, and then the flux at another point, and typically when one's considering salinity in freshwater, you use the Bering Strait, because that's the choke point, and we know rather well what's going on there. So we look at the freshwater fluxes through both of those points, and then we can think about the divergence between those two, and then you're accessing the information about how much freshwater is going into the ocean. Okay, so I meant to say as well, please do ask questions by going on very quickly. What's those? Sorry? Right, so why do we care about the freshwater fluxes? Well, one of the reasons that I care about it, and spent quite a long time working on this, is that the freshwater fluxes drive salinity changes and buoyancy changes at the ocean surface. These drive buoyancy-driven circulation, and ultimately this leads to water mass formation. So I'm particularly interested in this in the Atlantic because the salinity budget of the Atlantic, and so this is a picture of salinity. It's I think from 10 meters, it's from Argo data, and just some global products. It does, it doesn't matter what exactly. It's just a surface salinity essentially. You can see the Atlantic has a massively high salinity, and it's this really high salinity that preconditions the Atlantic, so that even as fresh water is added in the north and the temperature is reduced, the heat is lost, it's this high salinity that allows the water to be dense enough to make North Atlantic seawater. So the salinity is really important in the Atlantic for this reason. And by looking at these kind of time series, we start to think about what controls the salinity in the Atlantic, what controls the salinity in the North Atlantic in these formation regions, and also start thinking about how this might change into the future, because obviously North Atlantic deep water is an important part of the climate system. Right, so how do we actually make this calculation? So we at 26 North, what we need to do is make essentially a pseudo hydro section, and we try and do that every 10 days. We do it every 10 days. So we take so we need a transport time series every 10 days, and we need a salinity section every 10 days. So we construct the transport time series using the rapid Mocha Western Boundary Time Series array. So this makes up the 26 North array and gives us the nice estimate of a much higher resolution. I think every 12 hours they produce for the MOC that we're kind of used to seeing now, but need to remind ourselves that these didn't exist at one stage. We take temperature and salinity data from the mooring. So optimally interpolated Argo product. So we use the optimally interpolated Argo product to both inform the salinity field in the interior, but we also use the temperature and salinity to give us a horizontal circulation. So we start thinking about what's going on in between the moorings in a horizontal sense, as well as exactly what's happening at the mooring. Okay, so and then finally, the last thing we use is repeat hydrography. So I'm just going to show you, this is a movie of our optimally interpolated Argo product. This happens to be temperature, and it started at 2000, and you can see the North Atlantic filling up. So this is now 2006, so it fills up basically in 2003. The main point of showing this is that I'm still quite excited to have movies to show, because it would be crazy modelers to have movies. So it's kind of remarkable now that we have enough data to be able to see this kind of stuff. So the final part of the puzzle of things that I use in this analysis is repeat hydrography. So 24 North has a long history of repeat hydrography. It was occupied in the IGY in 1957, it was occupied in 1981, 1992. Molly was there in 1998, and we've occupied it in 2004 and 2010 also, and are due to go back at the end of 2015. So in this analysis, I use the repeat hydrographic data to look at the structure of the salinity fluxes on the section, work out what assumptions it's reasonable to make, because I do have to make assumptions in this analysis, and also look at what the uncertainty associated with the assumptions are. So that's the part that repeat hydrography plays. Okay, so how do we actually calculate the freshwater flux? So I've now got a velocity field every 10 days and salinity field. So I can split the section up, and I just use exactly the same regions as was used in the overturning calculation from the 26 North array, except that I further split the interior into this almost invisible blue colour, which is deeper than 1760 decibels and shallower than 1760 decibels. So this is split at 1760 because that's the depth that we reliably get Argo data to. So this part is informed by Argo, and this part, this part is not informed by Argo because it's deeper than it, and this part is. Okay, so we have an 8.5-year time series. The data has now come out of the array up to 2014, so there's another 18 months of data from the array now, but we so most of it goes to 2000. It just happened to be for this time period. There were some floats that didn't go that deep, so it was just so we got uniform. We could kind of interpolate or something. So it's just that's the number that it happens to be. So an 8.5-year time series. The thin lines are the every 10-day lines, and the heavier lines are just a 5-day smoothing to help the eye, basically. So we have a Florida Strait component, which is large and positive. It's about 30 Sturgeon times about 36 PSU. So that's the transport weighted salinity in the Florida Strait. And then the other components are smaller, largely because they're entirely almost because there's much more velocity, so much more the transport associated with them. So the Florida Strait is largely compensated by the interior shallower than 1760, so that's the recirculation, and also the interior deeper than 1760. Okay, so at each time point, we add together all of these components, that's the whole section. We then constrain that to be southward negative 26 Sturgeon PSU by adding a single volume flux at the section average salinity. So 26 Sturgeon PSU is what goes through Bering Strait, and the assumption that we're making there is that there's no salt diversion. That doesn't mean that the salinity can't change, but it means that if the salinity changes, we have to add fresh water. Okay, so and then so once you've made that correction, the net volume flux across the section is the freshwater flux. Okay, so this is the time series of the freshwater flux. It's the same 8.5 years. It's a volume flux in spur ducts. Again, the thin line is every 10 days. The heavier line is 5-point smoothing. So it's always negative. The flux is always going southwards across the section. What else to say? It's very variable. There's a large peak here, which is associated with the slowdown in the MOC that happened in 2009, which I meant to point out on the transport curve, but forgot, and we'll come back to that later. The most meaningful part about this time series, as I explained at the beginning, is not necessarily the flux across the section, but the divergence of that flux between the 0.8 spur ducts that go through Berwick Strait and the flux that's going across 26 North. So on average, the flux across 26 North is minus 1.17 spur ducts, which means that on average 0.37 spur ducts is being added to the freshwater is being added to the system between Berwick Strait and 26 North. So this is so the freshwater is being added, so it's equivalent to evaporation being less than precipitation or decrease in freshwater storage, which means an increase in salinity. So it's equivalent to those two things. Okay. Any questions? Yes.
Can you elaborate on what assumptions you make in the detail?
Right, so what I do there is I take moorings from the rapid array and just do a linear interpolation between those. So there's no horizontal flux there, just the overturning flux, and that's exactly the rapid flux. And there's a linear interpolation of the salinity field. And then, by looking at multiple repeats of the hydrographic section, I work out what the uncertainty is associated with that. And
so you assume a static salinity field?
No, it's not static because it's related to the moorings. And then also because the moorings don't go quite as deep as the section, I add a temperature and salinity deeper than that, deeper than the deepest point in the mooring, which is related to the hydrography, and then I move that according to, I offset it by the anomaly at the bottom of the moorings. So I fill in the bottom bit and just join the lines of those two bits. So there's no horizontal, and the overturning is simple. And basically all on the rapid moorings, and then the bottom bit is from hydrography. But looking at the repeat hydrographic sections and the salinity, the structure of the salinity fluxes in those, it's not important. But making those assumptions. Right. So there is a seasonal cycle in the freshwater flux. It's not this is what it is. It's not the most convincing seasonal cycle ever. It's there, that's what it is. It's slightly less fresh water going southwards in the first half of the year and more in the second half of the year. I wouldn't say anything very much stronger than that. So this is the average of days a year, and this is the standard deviation for the whole time series. Okay, there is significant interannual variability. Many of the years, right, so this is the whole time series, averaged on years, where we start the year in April because that's when the beginning of our precious time series started. So it runs with our financial year. Anyway, so we get 8 full years. These are the values of the freshwater flux in each of those years, and there is the overturning that David Sneed wrote up earlier with the MOC. So the freshwater flux is generally 1.1, 1.2, and then goes down to 0.96 here. You know, that stands out. And then that was the year that there was the large downturn in the MOC where it reduced by 30%. Okay, so we see that it's related to the MOC. We can split the freshwater divergence up into components. So these are the three components of freshwater flux: the horizontal free flow and the overturning, and then this is the total. So this is the divergence. So it's the full time series relative to 0.8 Burduck. So this is why it's now averaging 0.37. The horizontal flux is small and positive, or medium sized and positive. So that relates to a recirculation flux. It's the Florida Strait going northward, and then the southward compensation of that being more saline. So it's the southward salinity flux, which requires fresh water to go north to balance it. It's not very variable. I was kind of surprised by how little variation there was in that. The overturning flux is the largest component, and it's the largest magnitude. It also has the largest variability, and it looks very much like the total. So this overturning flux is associated with more saline surface water going north and fresher water coming southwards. That's the northward salinity flux and the southward freshwater flux. So the overturning flux circulation transports freshwater southwards. The final component is the through flow, which is because this is a divergence. It's the change in it's a change in the flow associated with a change in the section average salinity. So this reflects the fact that the flow through Bering Strait is fresher than that going through 26 North. So that requires it requires the water to become more saline, which requires this much fresh water to be removed. This doesn't have standard deviation on it because it doesn't vary, and even when I put time varying average salinity field in there, the standard deviation is 0. So for those two decimal places. So the overturning obviously important in setting the freshwater flux at all time scales. Okay, so we can formalise that by looking at a relationship between the MOC and the freshwater flux. So the MOC is increasing along this axis, and the freshwater flux becomes more southwards down here. So with increasing overturning circulation, you're sending more salinity northwards, and so more freshwater southwards. This is the relationship, so that every 1 square drop increase in the MOC, you get a decrease or a more southward freshwater flux of 0.047. This describes 84% of the variance in the freshwater flux in the MOC. So we can also do this calculation in heat flux. This has been published with, by Bill Johns and others. So this gives us similar calculations. We've got the same freshwater flux number here, and then the heat flux increases with an increase in the MOC. Okay, and so the point of showing you that is because we're now going to look at the downturn in the MOC and think about how the decrease in volume going northwards affects the heat and freshwater budget northwards. Okay, so in 2009 there was a slowdown in the MOC. So this is the MOC time series, the high resolution time series here in grey. This black is an annual smoothing of it. So this is the downturn which stands out very markedly there. The This red line here is an average from 2005 to 2009, so that kind of shows you what we thought was a typical MOC until they brought these dates back. To look at what's going northwards, we have to think about the size of this event, and the way we do that is by accumulating the difference between this line, extrapolated, and the raw time series. So if we accumulate those two things, the red line is accumulated here and is a straight line. The black line varies around that a bit while it's being kind of average as normal. And then in 2009, it starts to diverge from it, and you can see it then diverges off. So we can look at the difference between these two lines, and that gives us the deficit in MOC. So that's the difference between the accumulation of these two lines. What it actually is just the area between these two integrations which go along. So it's just to estimate the size of the event. So this is that deficit accumulated. So this is in further up years. And if you go along, in 2009 it starts to increase, and in 2010 it got to about 8 further up years. After that, it's still decreasing, and this signal here is associated with the kind of longer term decrease in the MOC that David Smith wrote about earlier this year. Okay, so we now have a deficit in volume transport going northwards, and we can convert that into a deficit in heat flux and fresh water, or equivalently salinity flux, by combining these with the with these numbers, basically, just converted into joules and kilograms of salt. So then we look north of the section. It happens to be in this box. It was a box chosen to avoid the boundaries and to avoid the Gulf Stream as well, because once you start integrating the Gulf Stream into an optimum interpolation, it, you know, whether it's there or not can make a very big difference. It adds a lot of variability. So what we've got here is the heat content in the within this box in the top 1,800 meters, and the salt content in the same box. So the thin line is every 10 days, the heat content in that box, and the heavy line is an annual average of that. When we're doing the optimum interpolation, we calculate all of this on density surfaces, and we interpolate it relative to a climatology, which we use quite a way because we like doing things on density surfaces because it keeps the it's slightly more faithful to the water mass properties. And we interpolate anomalies because then you don't have to reconstruct the mean field, and the mean field is, you know, that's information you know, so you don't have to relearn it every time. So these are all in anomaly space, which is why they're kind of around zero. But it's what this means is that during the first 5 years of the time series, the temperature was higher than the climatology. So it was the warm ocean. During the turn down, it decreased into below zero, so relative to hydro rate it was cold, and then it recovered some. In salt, we can see that it was a salty ocean, so it's the same. We use the same structure of anomalies to do the salt budget as well. So you can see it was a salty ocean, and then it went down to nearly zero, so nearly back to the climatology. These red lines here show the deficit in salt and heat being transported northwards associated with the turn down in the MOC. So those are the numbers that we calculated from the slope of the sensitivity to the MOC combined with the deficit number of 8 further up years. And they've just been put in the middle of the the turn down event, so that where they are on the x-axis isn't significant, but there's an incredibly close correlation between the size of this event and the size of the deficit in heat content and the size of the deficit in heat being transported northwards. And so the interesting thing about this is that the circulation is implicated in varying the heat and fresh water, the heat and salt content in the North Atlantic, and it's not just all immediately interacting with the atmosphere. There's some influence of the ocean and also some memory in the ocean. Okay, I'll just talk about that now. Okay, so now just going back to freshwater again, and just speak a bit about uncertainty. So we did a very careful analysis of the uncertainty for each of the components that go into the freshwater calculation, and here they're ranked from top to bottom. So Florida Strait is the most significant. The interior deep, so the kind of assumptions that I was saying about is the smallest, and then the barotropic compensation is associated with the offset and the salinity at which that occurs. So all of these, there are two elements that go into each of these uncertainties, one associated with uncertainty in the salinity field, one associated with uncertainty in the transport field. The uncertainty in the transport field is always the largest of those. The largest contributor to the uncertainty is the Florida Strait transport, and that's not because it's not measured very well, because it is, it's because the calculation is massively sensitive to those estimates. So and if they weren't as good as they are, we'd be doing an awful lot worse. So the total uncertainty is 2 spurgeon PSU in the salinity flux, or 0.06 spurgeon in the freshwater divergence. That's on each 10-day estimate. If we the annual averages are better than that and are about 0.02 spurgeon in the freshwater divergence.
Is it an indication?
Yes. Okay, so I just want to talk a little bit more about uncertainty and say something about Bering Strait, because that's one of our main constraints. And actually, one of the things I should have said here is that Bering Strait, the uncertainty associated with Bering Strait really isn't that big, and that is something that is somewhat surprising to people when I read it. So the uncertainty is dominated by uncertainty in the Florida Strait volume flux. And the elements of the uncertainty, so I've just put here again the freshwater flux, and then this is the freshwater flux put into components. The uncertainty projects differently onto different components of the freshwater divergence. So whilst the uncertainty on the mean flow through Bering Strait has components in the overturning and horizontal freshwater fluxes, they're completely insignificant, and so all of it goes into the free flow component. And what that means is that if we're getting the transport through Bering Strait wrong, that would, this is Bering Strait, that would move this down, for instance. What happens is that this also moves down by almost exactly the same amount. So although you will change the freshwater flux, the divergence remains almost unchanged. So there is an uncertainty, it's small, and it all goes on to the free flow component. Okay, so I'll just say something about the the constraint that we use through Bering Strait is 0.8 spurgeon at 32.5 PSU. This gives us quite a small uncertainty of 0.5 PSU or 0.02 spurgeon. So although that accounts for the seasonal cycle that we know exists at Bering Strait, but we use a single constraint. But I'll just show you how that seasonal cycle projects onto the freshwater flux estimate. We do take this into account in the uncertainty already. Okay. So this is from Rebecca Woodgate's work and co-authors. This is the transport through Bering Strait. So the average transport is 0.8 stirrups, but seasonally it varies from minus 0.4 to about minus 1.3. This is the seasonal cycle in salinity, shown here. There's another lighter line here, which is what we call the adjusted salinity, and that's related to the fact that when these measurements are made, they're all made near the bottom, and the upper ocean salinity is thought to be a bit fresher. So there's two sets of measurements. So there's one which is thought to be more realistic. Okay, so that, and then this is 32.5. So that's the average that we use at the moment. So if we combine those two, we get salinity flux, which varies seasonally. This is minus 26. This is what we use. And then if we apply the seasonally varying salinity flux instead of our straight minus 26 at 26 knots, this is the difference in the freshwater flux. So this is really big. It goes from plus 0.4 to nearly minus 0.5. So that's a really big effect on the freshwater flux. But if you look just to the left, you can see the change in the volume transport through Bering Strait, and these are almost identical. So it's just speeding up the spin wheel, not adding anything massively to it. So when we subtract these two, because it's the divergence, but it's important, not the actual freshwater flux, we get a very much smaller signal. So this is the signal associated with the freshwater divergence, or the equivalent freshwater flux, of course, here. And then the light line is that associated with the adjusted salinity. So the seasonal variability affects the freshwater divergence by minus 0.03 to plus 0.4, and it's a slightly larger range if you use the adjusted salinity. So it has an effect on the freshwater divergence. This is accounted for in the uncertainty rather than constraint, and it projects only onto the true focal height. Right, so I just wanted to give you a little bit of context for these numbers that I'm giving you. So this is from Susan Whittle's chapter from the first growth book, early this millennium. Right, so the lines here are integrated reanalyses and data products integrated from the North Atlantic southward. So it's the integrated freshwater divergence. So when that's getting more negative, it's equivalent to precipitation. As it gets more positive going southward, it's equivalent to evaporation. And one of the points to take from this is that once you get into the South Atlantic, there's a massive spread here. So this accumulates all the uncertainties, and there are large uncertainties associated with these things. What I've added to Susan's plot is the output from this study. That's minus 0.37, which kind of lies below their lines, below these lines. And I've also added a, I don't suppose I can call it recent anymore, it's from 2010, estimate of which evaluated multiple products for precipitation and evaporation and came up with this combination as being optimal, giving this curve, and then there's two other estimates here that we've recently made from hydrography in Southampton at 24 and 36 north. So, what are the things about this? So one of the reasons I like this Shanza estimate is it's one of the few estimates that give us a very near zero divergence in the South Atlantic, which is something that we've been observing in hydrography. So this estimate was Peter Thornton and Brian King's estimate from the A11 section. So we've been observing this near zero divergence in the South Atlantic. There are other estimates that aren't on this plot for, persistently for quite a long time now. So it's nice to see a surface flux integration giving that. What are the other things? So, and then the other thing is that it seems that the modern estimates estimates in the North Atlantic kind of seem to lie beneath these. So that's curious as to whether or not that's associated with the constraint that's put on it, or the assumption that's made about what's going into the Arctic, or whether there's real variability. So this estimate, for instance, which is one that I can look slightly more deeper into, comes from Hall and Bryden in 1982. That's their analysis of the 1957 IGY section at 26 North. When we look at that in more detail, because it's broken down really nicely in their paper, I can tell that what's the difference between the analysis that they're getting and the components that are going into the freshwater flux and what we're doing is all in Florida Strait. Okay. So this is a picture of the time series of the estimate of transport weighted salinity in Florida Strait. Okay, so the transport weighted salinity takes account for the fact that the transport is highest at the surface where the salinity is highest. So when you want to multiply something by transport, you use a transport weighted rather than an area weighted property. Actually, the area weighted salinities kind of show the same, have the same structure. So, that's what we like to use in these calculations. This cloud of points here is the estimate that Zoe Flux and Chris Minan made last year now. And their mean is 36.2 that I've used in my calculations. That mean has a standard deviation of 0.049. I think there were 32 estimates there, and they come from about the last decade. Okay, so the other points on here are all from hydrographic sections. So 2010, 2004, they lie within this cloud of points. This is 1998. 1992 has 2 points, which are kind of far apart. There were some issues with the 1992 section. They had a problem with the echo sounder, so CTD didn't go right to the bottom. So there's been some extrapolation there, and I suspect that this kind of separation of these 2 points is associated with exactly how that's extrapolated. This is the 1981 section, which comes from 2 different authors. And then this is the Hall and Bryden section. They actually combined in their 1967 interior section a 1974 section of Florida Strait. So the numbers after these in brackets are how many of the modern standard deviations this mean is away from the modern mean. So it kind of looks like it's increasing. You know, this isn't kind of conclusive evidence of that. What it is evidence of is that the transport weighted salinity that's been used in the historical freshwater fluxes is changing. So, and this calculation at the bottom just shows that it's significant. The change in the transport weighted salinity is 0.31. This operates on about 30 spur-ducts, which flow through Florida Strait, so that's just over 9 spur-ducts TFU. And if we divide that by the section average salinity, that equates to 0.27 spur-ducts. And that's the change in fresh water, which is almost all of this very near zero and our 0.37. And almost all of that is accounted for by the different transport weighted salinity used in Florida Strait. Okay, so in summary, we've derived an 8.5-year time series of the freshwater flux at 26 North. We've shown that variability in the freshwater and heat fluxes, you know, we already knew about the heat fluxes, but they're dominated by variability in the MOC. We've related those changes to the MOC to the variability in the upper ocean heat and salt content, and shown that the Florida current is related to variability in the historical freshwater flux estimate. Right. Oh, so this is largely written up in these 2 papers. And as well as kind of acknowledging and thanking all of my co-authors, I just wanted to say that this project has has relied on many very large programs, including the Rapid MoCA Western Boundary Time Series, crucially at this latitude, but also Argo for filling in the gaps, and GoShip for kind of underpinning the whole thing and telling us about structure for the whole section. So I just wanted to specifically run those through. Okay, before I stop talking, I just want to tell you about the next round of funding in the UK associated with RAPID. So the UK's contribution to this 26 North Array has recently had another call for proposals aligned with RAPID. One of those was to look and think about biogeochemical fluxes across 26 North. Okay, so myself and my collaborators came up with Atlantic biogeochemical fluxes, or ABC fluxes. So our aim is to instrument the Rapid MoCA, I missed what the Western Boundary Time Series array to calculate carbon and nutrient fluxes across 26 North. Okay, so this is a collaborative project. I'm leading it from the National Oceanography Centre in Southampton. It includes the Carbon and Modelling Group at the University of Exeter, the Modelling and Observation Groups at Plymouth Marine Laboratory, also the University of Southampton, and the Met Office and NOAA are project partners in there. Okay, so right, so we've got this is kind of one of the, I really like these plots. So they kind of motivate me to write these incredibly complicated proposals. We were funded, by the way, so this is all happening now. So this is the anthropogenic carbon uptake. So this is the air to sea flux of anthropogenic carbon. It's an estimate of that. Okay, so you see hot colours in the Southern Ocean and in the North Atlantic. So that's where anthropogenic carbon is going into the ocean. This is a picture of anthropogenic carbon storage. So this is the top to bottom inventory of anthropogenic carbon in every column of the ocean. Here the hot colours are largely in the North Atlantic. So the difference between these two plots is circulation. Basically, anthropogenic carbon is being taken out of the Southern Ocean where it's going in and being put somewhere else. And the North Atlantic compensates for that. So the difference between these two plots is the circulation, and the Rapid MoCA Western Boundary Time Series array at 26 North is really perfectly positioned to sample what the fluxes through the ocean of anthropogenic carbon are, what controls those fluxes, what are the modes of variability, and crucially, how might that change in the future. So this project has 3 work packages. Well, no, there's 4 actually. Anyway, it has. We're gonna. So this has a very similar philosophy to the freshwater fluxes. So it's about estimating a anthropogenic carbon field every 10 days, combining that with a transport field and working out what the anthropogenic carbon fluxes are. We'll also be doing it for other biochemical variables. We're going to do that using existing data, and those are calculations that we're working on at the moment. We're also going to be making some new observations. So this is the array. The colours is an anthropogenic carbon field. So it's high at the surface, goes up to about 80, and low goes down to near 0. In the bottom, all of these blue colours are less than 10 micromoles per kilogram. The vertical lines are the rapid moorings, and the dots are the new instruments that we're going to be putting on. So the white ones are oxygen sensors. At the surface, there are 3 points here where we're going to be putting PCO2 and stage sensors, and we're going to be putting samplers co-located with each of those, and a sampler at depth associated with the Western Boundary as well. So those are the new observations that we're going to make on the array. We're also going to be adding some oxygen-enabled deep and bio-Argo floats in the same way we did with the Argo floats for the salinity fluxes, to add information about oxygen in the gap between the moorings. And then the final element, which is NOAA's, the part NOAA plays in it, is sampling of the Florida Straits on the 40 cruises that you ran here for nutrients and carbon. Thank you.
Thanks for the talk. We use the Bering Strait as a constraint.
Yeah.
So the freshwater fluxes in the Arctic, the Russian rivers, and the seasonal freezing and thawing is not significant.
No, it is, and that's all in there. So this is a kind of quite accurate, but an entirely bulk measurement. So the net effect of all of those is in there. Actually, what it is what we see at 26 North. So some of those we might not see there. So it's a bulk estimate, it's a single number that integrates all of those processes.
But they are happening downstream from the Bering Strait.
Yes. Yeah, so it's bulk.
I had a question about the relationship between the MOC and the freshwater flux.
Yeah.
When you looked at the sections, did you find a similar relationship?
I could plot those on there, I haven't.
A similar slope or similar?
Well, so the section would give us one number. Yeah, so I just haven't looked. So it would be all of them together. I would have to, I'd need more points to see, and so I just haven't looked.
So when you look at that relationship, you said that you know using like 84% of the vines
Yeah.
in the regression. So can you just remind me what are the type of data you put in that explain like the rest of the vines? So is it like the algal field?
Well, and no, so the so the horizontal flux isn't in this. So anything that's not associated with the MOC, there'll be this would be variability in the horizontal flux would be in there. I did try and correlate the residuals with the gyre circulation, but that with the strength of the gyre, but that didn't work.
So for the new project, are the oxygen sensors already out?
There are a dozen oxygen sensors in the western boundary.
When do you plan to put the other?
Next, this time next year, a year from now. So these ones here, 12, are already out. Oh, don't.
Is there any reason that you don't expect the carbon flux to also be dominated by the ocean?
No, it absolutely is. It absolutely is. But the carbon flux, the antigenic one, it has it's increasing. You know, so as well. So there is an element that so that's kind of an inventory issue. But so there's that. The other thing is that carbon isn't just it's not just flux around by the physics, Lisa. So you know there are other things, other annual cycles and controls on it that you know we don't know about yet. We haven't got
So yes, I mean, so the total carbon flux will be androgenic flux, because that's bound to the top. You can see it right, the top 1,000 meters, and that's where you see from the opposite direction. It's a very interesting question.
Yeah.
Interesting.
So no, that may do. So we're kind of working on this now with the data that we have, and those residuals kind of so vivid. Freshwater, so those residuals do just march up. So the, for the same overturning circulation, the